Hello everyone, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about indifference pattern and also we discussed about Young's double slit experiment. It's very important to remember the condition for dark fringe and bright fringe in the indifference pattern. It will be useful for your numericals. Today we are going to discuss another concept of this chapter, that is diffraction. We will discuss more about the diffraction phenomena and the experimental setup to obtain the diffraction phenomena. So, I hope you remember the experimental setup for Young's double slit experiment. If you close one of the slits in the Young's double slit experimental setup, you can easily observe the diffraction pattern on the screen. So, in a diffraction phenomena, there will be one slit. Okay, so if you want to observe a single slit diffraction pattern, just close one of the slits in the Young's double slit experimental setup. You will observe diffraction pattern on the screen. So let's discuss more about diffraction and also let's discuss the conditions for maxima and minima in diffraction pattern. So what do you mean by diffraction? Bending of light round the corners of small obstacles or apertures and its consequent spreading into the region of geometrical shadow. That is diffraction. So let me explain the same thing with the help of an example. Here I have represented an obstacle. This is an obstacle. Okay. Now light rays are coming like this. Okay. From a source. From a distant source, light rays are coming like this. And here, the light rays cannot pass through this region as an obstacle is placed here. Okay. But at the same time, when a light ray passes round the obstacle, it has a tendency to bend round the corners of that obstacle. And this obstacle is very, very small. Okay. For our convenience, I have just magnified it. So what happens? The light ray will be passing through the sides of this obstacles, sides or corners of this obstacles. So if you place a screen here, we can see a bright area on the screen and also dark area on the screen. So on the screen here, we can see a shadow part, and this shadow part is due to this obstacle, and so this is the shadow of that obstacle, and this shadow is observed due to the bending round of light around the corners of this obstacle. Okay, so light ray will bend and move like this, and here on the screen you can see brightness because light is reaching on the screen in this portion. So brightness is obtained on the screen because light ray directly reaches the screen like this. Okay, so this bending of light around the corners of small obstacles or apertures and its consequent spreading into the region of geometrical shadow is known as diffraction. And this is the experimental setup of diffraction. See, instead of two slits, they have used only one slit here, and this is the pattern observed in the screen. Okay, so here at the center we have a maximum, that is called the central maximum, and on either side of the central maximum the amplitude of the wave is decreasing. That means the intensity goes on decreasing on either side of the central maximum. So this is the pattern observed on the screen, or this is the peculiarity of the diffraction pattern. Do you remember the indifference pattern? Indifference pattern looked like this. If this is the intensity axis, then indifference pattern in the indifference pattern at the center we have maximum. So this is the central part O. On either side of the central maximum we have alternate dark and bright fringes but with same intensity. So here This was the indifference pattern. But what was the diffraction pattern? Diffraction pattern looks like this. At the center, there is a central maximum, and on either sides of central maximum, the intensity goes on decreasing like this. See? Okay. So this is the major difference between the indifference pattern and diffraction pattern. So it's a very important question. They will ask you to cite the difference between indifference and diffraction pattern. Next, let's try to analyze the diffraction phenomena mathematically, and let's try to find out an expression for angular width of central maxima and also the condition for maxima and minima. Okay. Children, let's try to analyze the diffraction pattern in a detailed manner. So here you can see the experimental setup for diffraction pattern. This is the source. Source produced the wavelets or wavefront, which is incident on a single slit, and this slit is very narrow, but for our convenience I have just magnified it. So the width of the slit is small a, that means the distance between the points A and B, that is small a, and we can consider the center point of this slit. So this is the center point of that slit, and let it be denoted by capital C, center of the slit, and we can just draw a dotted line through this. Okay, so C is the center of the slit. Now from the point A and from the point B, the waves will travel. Consider a point P on the screen. So this is the screen. This is the screen. The screen is placed at a distance of capital D from the slit. From the point A and B, waves are traveling towards the screen. Consider a point P on the screen, which is situated at a distance of x from the point O, and O is the center of the screen, and it also corresponds to the center of that slit. Okay, so consider a point P on the screen which is at a distance of x from O. Since single slit is used here, diffraction pattern is observed on the screen. Okay, and this is the diffraction pattern. So first we can discuss the path difference of the waves from A and B. What is the path difference between the waves originated from A and B? So in order to find out the path difference, just construct a normal, or just draw a normal like this. Okay, and this normal meets the line BP at N. Okay, so if we consider the path traveled by the waves from this point onwards, this distance, that means NP and AP, both are same. So what is the extra path traveled by the waves coming from BN? So what is the path difference between them? BN. This is the extra path traveled by the waves coming from B. Okay, so path difference is equal to BP minus AP. BP minus AP is BN. So that is the expression for path difference. Path difference P is equal to BP minus AP, that is equal to BN. And we should find out an expression for BN. For that we must consider this as a right angle triangle where this is theta. Okay, this is the angle theta, and find out sine theta from this triangle. Sine theta is opposite side by hypotenuse. Here opposite side is BN and hypotenuse is AB, and this AB is equal to A. Okay, so sine theta is BN by A, therefore BN is equal to A sine theta, and our path difference P is BN, so we can write path difference P is equal to A sine theta. So this is the expression for path difference in diffraction phenomena. Okay, now we can explain about the central maximum. Okay, central maximum is obtained at the point O on the screen. So what is the peculiarity of this point? See, if we consider the waves traveling from A and B towards the point O. So the waves travel from A to O. This is the path traveled by the waves coming from A. And here the waves travel from B to the point O. And if you consider the path AO and BO, you can see both are equal. So path difference is 0 here. And whenever path difference is 0, path difference means there is no difference in their path. Both the waves coming from both the points A and B travels equal distance in order to reach the point O. So there is no path difference between the waves reaching the point O. So path difference is 0, and whenever path difference is 0, the fringe obtained at this point will be bright fringe, very bright fringe in fact. So this is central maximum. This bright fringe is called central maximum. So central maximum is obtained at the point O, where the path difference between the waves coming from the points A and B is 0. Okay. Now next we can just explain the formation of secondary minima and secondary maxima. Okay, so what is secondary maxima? The maxima coming soon after the central maximum is secondary maxima. So this is a secondary maxima. This is a secondary maxima. Similarly, this is the secondary maxima. This is the secondary maxima. These are the maximas following the central maximum. And what is secondary minima? The minimas following the central maximum. So if we consider, this will be our secondary minima, and this is our secondary minima. Here this is our secondary minima. So this is the secondary minima, this is the secondary minima, like that. And again we can give number to that. See, this will be the first secondary minima. This will be the second secondary minima. Here also this will be the first secondary minima, second secondary minima. Similarly, this is the first secondary maxima. This is the second secondary maxima. This is the first secondary maxima. This is the second secondary maxima. Okay, so this is the position. This is about the position of the secondary maxima and minima. First we can explain the formation of secondary minima. So here central maximum is obtained when the path difference Pn is 0. Okay.